So welcome everybody to this ERI Science Hour organized by Work Package 6. And so today Eneko will be presenting his work about analysis of high resolution coupled model, analysis of some aspect of the AMOC and its variability. And so Eneko, I'll let you introduce yourself and start sharing your screen.
Yeah, sure. Let me share.
So you are a PhD student, right, at BSc?
Yeah, I am a PhD student at the BSc. Are you in my screen, right?
Yes.
Yes. Okay, so yeah, I am a PhD student at the Barcelona Supercomputing Center. I am currently in the middle of my second year of the PhD. And yes, so I have been working with high resolution models, particularly with the high resolution version of ECR, which is the eddy-rich one. I will show you now what will be the results for the first chapter of my thesis. I mean, we start working on a paper about this, and it's how the eddies, or how the resolution, because we are with 3 different resolutions, impact on the deep water formation processes, and how it's linked to the AMOC. And yeah, as you know, this is the 8th ERI Science Hour. And just to know a little bit of the project, for those that who are not part of the project, there are plenty of colleagues here in the room with me as well. So it is a public project funded by the European Union, United Kingdom, and Switzerland. I also, as a PhD student, I have a grant from the Spanish Ministry, and some of us, we are also working with funding from the Spanish Ministry for the STREAM project. And I wanted also to thank all the colleagues that have been working with me. Here are some of them, but obviously there is much more people that has helped me, that has given me some feedback and everything. So here you can see the colleagues from the project, like from the data team that has been helping with the summarization, like my supervisors Edu and Pablo. Eduardo, it's now on MPI, it's not anymore on the BSc, but and let's just start. So I wanted to start with this new that probably most of you have seen, and maybe before that the actual paper that it's referred to. So this Atlantic Ocean circulation tipping point, which is about the meridional overturning circulation tipping point. So there is this open question nowadays in science if the AMOC will stop or not. So this paper, they do a very interesting approach. It's got out 2 weeks ago, and they use the CSM air system model just to develop some kind of indicator. Then later they use to check with the observation if we are close to the tipping point or not. The only thing that the version of the model they use has 1 degree of resolution, horizontal resolution in the ocean, and 2 degrees on the atmosphere. So this means that this model has no eddies. So it's not an eddy-rich model, eddy-parameterized one. Yeah, so I think it's okay. We know that eddies are important, but I wanted to give a small introduction for those not familiar with them. I mean, most of the people in the ERI project maybe are already familiar with the eddies. But for those who not, these are some kind of structures in the ocean. They are part of the ocean mesoscale processes. They are something like 100 kilometers length scale or smaller, and they last for time scales of 1 month or smaller. And they are, we know that they are really important in the transport of water masses to remote regions, like, for example, different salinity and temperature water masses. This impacts the mean state and variability of the ocean, which is one of the things we are studying on work packages of the ERI. And my work, it's like, okay, when the mean state and variability of the ocean is changed, this will impact as well on the deep water mixing, and thus on the AMOC. So there were like several studies about with this kind of eddies. So we can have here 3 different resolutions that Alice Marzocchi used in her paper. That they have on the top one we have the standard resolution, which is 1 degree of the ocean. On the middle we have one middle resolution, which is 0.25 degrees on the ocean, and on the bottom we have the high resolution, the highest one, which is 1/12 degree on the ocean. So we have eddy-parameterized model, we have an eddy-percent model, and we have an eddy-rich model. And they found out that the bias was corrected when using the higher resolution ones. Then we have some other studies, for example, this one from Toe and Koenig, where they saw that when going to higher resolutions, we have reduced the bias in the vertical profiles in the Labrador Sea, but we have some kind of very deeper mixing for those models, which is unrealistic. So not everything could be good. We have this paper also from Sortiria Georgiou, where she used a regional model for the Labrador Sea, ocean model, and they saw that eddies are really important in interchange of interior and boundary water maxes in this sea, which is also very important for the deep water mixing. And the last one, I wanted to mention the one from Eduardo Moreno, that where they saw that when having eddies, the Gulf Stream bias, the Gulf Stream position was corrected, so they reduced the bias on the position, which shifted to the north, so we have more heat reaching the north of the Atlantic. And also, as the resolution on the atmosphere in this case is an Earth system model, both ocean and atmosphere, as the atmosphere was already higher resolution, there was better interactions between the air and the sea, which led to increase in the rainfall over the northern Europe. So these were some examples. So eddy is about this, about having the eddies. It's a European eddy-rich Earth system model project. So, but it's not the first project with this high resolution, and I want to go back to Primavera, which was one of the first projects that tried to do that. So Primavera was running from 2015 to 2020. And this is, for example, the output from the Hadrian 3 family models. We have again 1 degree in the ocean, 0.25, and 1/12 on the right, and with different atmosphere resolutions as well. So it's also an Earth system model. It's and we can see easily how the dynamics of the ocean surface change. With the resolution on the top, on the right, we have much more fine structure than on the other ones. So, which are the models we worked with? So we work with ECR3 model, but with a special version prepared for the Primavera project. That's why the P, ECR3P. So the standard resolution that is similar to the one you have on the previous plots, it's 70 kilometers on the atmosphere and 100 kilometers on the oceans, and this means 1 degree. So this is an eddy-parameterized model. Then we have an eddy-percent model, which is 35 kilometers in the atmosphere and 25 kilometers on the ocean. And then we have the eddy-rich version of the model, which is 14 kilometers in the atmosphere and 8 kilometers in the ocean. Obviously, the resolutions are not the same in all the globe, so it depends on the latitude and the position, but it's an average idea for the mid-latitudes. And each point here represents 10 times 10 grid points on the model, so you need to multiply each point 100 times to have the real grid, which is much thinner. So with these 3 models, we use the HighResMIP protocol. This protocol developed to the high resolution model intercomparison project. We run an anti-50 control experiment, which means taking the forcing of 1950 just to only study the internal variability of the Earth system. And then we have 76-year-long experiments In fact, the original experiment were longer, but we still have some model drift because the spin-up was not enough, so we reduce a little bit more the longitude of the experiment, of the data we are going to analyze. For those not familiar with the dynamics in the North Atlantic, that is where I am going to go. So I take this figure from Birds and Payne from 2016, where we have the two main gyres we have in the North Atlantic. So we have here on the east of Greenland, the Labrador Sea. On the west, sorry, on the east, we have the Irminger Sea. This is the subpolar gyre, so all these blue arrows are this kind of gyre we have here. Down here to the south, we have the subtropical gyre, which goes on the opposite direction. This is clockwise, and the subpolar gyre is counterclockwise. And then we have some special land parts like Cape Farewell in the south of Greenland, Newfoundland in the east of America. We have Flemish Cap here, which is where the continental track ends of North America. We have Cape Hatteras, that it's also very important for the AMOC. We will see later. So just I want to give an overview of the region. So what is the idea of our analysis? So okay, we have some atmospheric forcing and salinity advection that could impact the subpolar gyre region, in particular the Labrador Sea, which is one of the regions where we have deep water mixing. So these two factors, they make force change on the mean stratification, which may provoke deep water formation or deep water mixing. This deep water mixing at the same time modifies the zonal density gradient, which could be translated on change to the AMOC, so variability of the AMOC. So we wanted somehow to study how all this process is connected and how the variability here ends up on the Atlantic meridional overturning circulation. So starting from the most simple analysis we can do, we just check the mixed layer depth climatology for March, which is the month where we expect to have higher mixed layer depth in the northern hemisphere, as it's the end of winter. So it's interesting to see that, as Koenig said in the paper, for example, in the HR, which is the eddy present one, present resolution, we have a very strong mixing, which seems to be unrealistic. Meanwhile, in the low resolution and higher resolution, we have some kind of same order of magnitude mixing, but in what is more interesting is that in the higher resolution, in the D-ridge, this mixing is really inside the Labrador Sea and seems to be more realistic. We can compare with the observations below. So here the mixed layer depth has been computed in a monthly basis just to make everything comparable. So it's not the instantaneous output from the model. But yes, in the case of the low resolution model, we have no mixing on the Labrador Sea at all because we have a sea ice bias there. And if we compare with more recent time, we see that we still have similar values for IN4, and here I include Argo, which is not totally comparable because the mixed layer depth is computed with instantaneous measurements, but there is also a bias that will happen on the observation as they are computed doing some interpolations. They could provoke some artificial mixing that won't be in Argo, but it's again not comparable because this is instantaneous and this is on monthly basis, so it's quite difficult to compare the mixing. So if we compare the standard deviation of the mixing, this gives us an idea about the variability of the mixed layer depth on March. We see that in the case of ECRth VHR, the rich one has a much lower variability than the other two models. And then the variability of the low resolution and middle resolution models, so the eddy-parameterised and the eddy-present one, it's quite more or less of the same order. Something more interesting to see here and in the previous plot as well is that we almost not have no mixing on the Nordic seas, opposite to the observation. So we didn't go really there to watch what's going on, as in the model seems that Labrador Sea and Irminger Sea in other resolutions are more important. So we took this box here. You can see in the first plot, the one on red, to take the average time series of the mixed layer depth and also the average vertical profiles. So these are the vertical profiles on that box, which is more or less the Labrador Sea, also taking a little bit from the Irminger Sea. So it seems at the first cut that on the first 100 meters on the surface, if you check the density climatology, seems that the one with less bias to the observations, it's the lower resolution model, the one in blue. But then if we check the salinity and the temperature, it's just the opposite. It seems that there is a much bigger bias on salinity and temperature on that model. So this means that the salinity and temperature bias are compensated, and we have no density bias. But then if we check the other two models, like they seems to perform better. Thought in the case of the HR model, the one with eddy present, the middle resolution one, we have less stratification, which also could explain the bigger mixed layer that we were seeing there, because we need to overcome less difference on the density to have a greater mixed layer depth. But they perform really, except for that, they are really similar. I will say that the VHR, it's quite better in some regions in the surface, but then depends on the variable. Maybe the HR is a little bit better. If instead of looking at the average, we do a regression of these average profiles with the mixed layer depth time series of March. So we can see how much anomaly on those variables we need to create 1 meter of mixed layer depth. So for example, we have here on the density how much kilograms or cubic meters of density anomaly we need per meter of mixed layer depth. So this, it's saying somehow, that the ECR 3PHR that's with a small anomaly on the density already creates a big mixed layer depth. Meanwhile, the other two models need bigger anomalies. If we check the salinity, the regression is aligned with the density, but in the temperature we have somewhere behavior, in particular in the low resolution model, which could be because it's much colder there due to the sea ice coverage and the anomalies of the water density with low temperatures. But then, if we move now to check the surface variable in the whole region, so in this case we have two different variables. In the first row we have the eastward wind stress correlated to the March mixed layer depth time series. And in the second row, we have the heat flux downward the surface. So this means the heat flux taken by the ocean correlated with the March mixed layer depth. So if we check out the first figure, and if we particularly focus on the HR and VHR, we have this clear dipole between north and south, which is a response to a now pattern. In particular, this positive negative is positive now. But as it is a correlation, this means that positive now could motivate enhance the mixing, while negative now could do the opposite, reduce the mixing. So to make it more sure, in contour lines, you have the regression of the pressure at sea level with the mixed layer depth time series, where you see also the now pattern, the positive now pattern. So in the north, you have negative correlation coefficients, while in the south you have positive. So this is not something new, it's something that I have already seen in some papers. So this now motivates this strong eastward wind stress on that region. which also enhances the heat loss on the Labrador Sea and Irminger Seas, which can be clearly seen as again in the two higher resolution models. So you have this big region which is significant with a strong correlation on head flux logs, negative head flux. And in the case of the low resolution, we don't have such a big area. And to make it more clear, you have in this contour line in the second row, it's the CS concentration at 15%. So we can see how the Labrador Sea in the low resolution, it's much more covered by CS, which is preventing it from losing heat when we have wind forcing. So if instead of wind, we check the advective salinity anomalies, we can see that in the three models we have some salinity anomalies that are the yearly salinity correlated to March mixed layer time series again. So we can see how from 2 years before or 3 years before, in the case of the very high resolution, we have these salinity anomalies more in the eastern side of the subpolar gyre, and then are being propagated to the western subpolar gyre until they arrive the west of the Irminger Sea, or in the case of the very high resolution one, also the Labrador Sea. These anomalies are affected by the subpolar gyre, which has the circulation has this direction, and it's something that's expected and also has some impact on the mixing. So we have both salinity anomalies and an atmospheric wind stress forcing this mixing. We know now the drivers, so now let's see which is the response to this mixing. So here we have the AMOC response to the mixing. So we computed the overturning stream function in sigma space, and we removed the Ekman transport and the Ekman return to remove any signal from the atmosphere, because as we saw that the wind stress is one of the drivers of the mixing, we could have this wind stress also forcing some circulation due to the Ekman transport. So to remove this Ekman transport, only have the mixing, we remove the Ekman transport to have a more clean signal. So in the case of the low resolution and also the middle resolution, the HR, we have more persistence in the signal, so we can see between 45 degrees north and 60 degrees north, and also densities of 36.8, this positive anomaly, which is significant, which lasts for 2 years, almost 4 in the case of low resolution. But in the case of the very high resolution, this anomaly produced by the mixing doesn't last so long. And in the case of the other two models, we have some kind of propagation seems to lower density, some signal that is sending upwards. And in the case of the high resolution, we don't see that. But we see in the 2-year lag, we see some kind of positive signal here, which is not really very strong correlated, but it's still significant. So this could be something that is propagated with waves. So let's see now what happens if instead of that we check the correlation of the mixed layer depth, with the overturning strength function time series. So we have taken the overturning strength function at fixed depth. In the first row, we have in the zeta space to 1050 meters. And in the second row, we have it in sigma space to 36.73 kilograms per cubic meter. So we correlate the density, so the overturning strength function at that level with itself, but at fixed latitude. So in the case of the zeta space, we take 45 degrees north, and in the case of the sigma space, we take 55. This is where the maximum, more or less, it appears in each space. So this gives us an idea of how the AMOC is coherent with itself. So how if there is an anomaly of the AMOC on 45 degrees north that is propagated southward, we will see a downward positive correlation, and it will be more diagonal if it takes more time to propagate, or it will be more vertical if it's more instantaneous. Also, if we see we could see in the other directions. So what we see is that the zeta space doesn't give us a lot of information. That's why previously I showed you the sigma space only. But also we saw that in the sigma space, seems that we have 3 different patterns for each model, which is some kind of interesting thing, no? We have like, in the low resolution model, seems that we have some kind of very fast propagation down to lower latitudes. In the case of the eddy-present model, HR, we have some kind of longer time propagation, which reaches 35 degrees north, 32. This is where Cape Hatteras is located. And in the case of the very high resolution, we have like really fast propagation and no persistence until 35. And then we have these small signals, a small significant here, which could be also the small signal we saw before, which could be some wave propagation. So this also could be aligned to what it's shown in other papers about the AMOC being propagated in advection time scales from the Labrador Sea until Cape Hatteras at 35 degrees north, but then from Cape Hatteras to the equator, it's supposed to be propagated, this signal, on coastal Kelvin waves, so it's much faster. But in any case, the time scales and the patterns are different. So then if we check now the density of 1000 meters, we also correlate it with the mixed layer depth, and we see how this density is evolving after the mixing. So on the low resolution model, seems that we have some significant signal on lag 1 and 2 on the Labrador Sea. So this means that the mixing that probably it's happening more in Irvinger Sea in this model, it's entering with the currents the Labrador Sea, so under the sea ice, which is something that has been discussed in some other studies. But in the case of the high resolution, we have the HR, we have this anomaly is more focused on the south of Cape Farewell, also entering the Irvinger Sea, and then with time entering in the Labrador Sea with 2 years lag. And in the case of the VHR, the interesting thing is that everything happens, or seems that happens in the Labrador Sea. So we have the anomalies on the same year in the Labrador Sea, and also exiting with the boundary current. It lasts for 1 and 2 years. We still have some kind of signal which is not at all significant. So what are the conclusions from this? Is that the drivers and impacts of the Labrador Sea convection are sensitive to the model resolution. So we have different results across each resolution. Then the mean Labrador Sea stratification and mixed layer depth are more realistic in the eddy-resolving version of ECR3P. So this is the ECR3P VHR. The North Atlantic Oscillation exerts a stronger influence on the Labrador mixed layer depth in the eddy-resolving and eddy-permitting version of ECR3P, so the HR and VHR versions are more forced by the NEO. The advection of salinity anomalies by the mean subpolar gyre circulation seems to also play an important driving role in the eddy-resolving one. So this means that we cannot only focus on one of them. In fact, they are related to different time scales. So the atmosphere is more on yearly to yearly variability, and the salinity will be more decadal or multi-year time scales. We we identify important differences across resolution, both in terms of speed and pathways of the propagation of Labrador sea density anomalies, in particular along the western boundary current, which ends impacting the coherence of the AMOC change across latitudes. So, okay, we have these conclusions, but what now? So in the paper I showed you at the beginning what they did to develop this kind of indicator. They did some small water housing about a long time. So we cannot do the same. We cannot do water housing for 1,000 years because the very high resolution takes a lot of resource to compute. But we can try to do a protocol of water housing for more short time experiments and trying to make it a little bit stronger. So we try to define a protocol and implement it. So we use an spatial and a seasonal distribute based on Weber et al. From 2019, which has this kind of distribution you see on the right, and also on space and on time. So it's mostly on summer. Then we use an ADLS setup. So this was 0.1 square drop distribute on average along all the coast and all over the year. So all over the year. So this is on average the water input. And we did 3 ensemble members for 21 years, branching out from the 1950 control, the experiment I was showing you before, but only for the very high resolution one, so only for the eddy-rich one, with 3 different AMOC states. So this was already implemented by Eduardo Moreno. This is, for example, how it looks like on the Nemo, the runoff from this water housing for July. What are the results of this water housing? So what you can see here, it's a 5 years moving average of the maximum AMOC on the depth space. So this is the overturning stream function on depth space maximum for each latitude. And we see, seems that we have some kind of trend to lower AMOC on the water housing, which is the one in orange. But we can see on the first row, we see at the 25 degrees north, which is close to rapid array. And on the second row, we have at 45 degrees north. But yes, seems that it's not so clear. For example, the third member in the case of 25 degrees north, seems that the water housing comes back where the control is. Seems that the trend can be mixed with the decadal or multi-decadal variability of the AMOC. So maybe we were not so successful if we wanted to reach a tipping point. We can see here, so if we take the last 5 years of the water housing experiments and the corresponding last 5 years of the control experiment, we do it so because we could have still small trends on the control. Nevertheless, we remove a lot of years. So if we take the last 5 years of the control experiment, so this will be 5 out of 21. So it's a quarter of the experiment, more or less. We see that for the 3 members, we have some kind of slowdown on the AMOC, which is more or less of between 0 and 0.5 and 1 square drop of a slowdown, but depends on the region. And also the third member seems that it's not so much, was the one that was giving issues before. And also we have this kind of weird, we'll say, or north continuous signal at around 35 degrees north, where we also have the Cape Hatteras, and where we also have this change on the pattern of the propagation of the AMOC, which is really interesting. That seems that this latitude is a place to really go deep and see what is going on there, because probably some other processes are taking part that we are not totally aware of. And so what now? So we will keep studying the water housing impact on the AMOC, but on the sigma space, because we saw before that sigma space was a better indicator. So we still didn't have time because these plots were published this week. The experiments just finished not so much time ago. So we will also investigate how the water fluxes ultimately influence the water mass transformation and the vertical mixing, and in particular studying the salinity anomalies propagated in the subpolar gyre. This is from those at the Max Planck Institute. I will be there from April to June doing a visit, so we may work together on that. And obviously anything else that comes to mind or you suggest or we see that could be interesting, we will work on it. So this part of the water hosting will be already my second part of the PhD thesis. So still a long time to go. So now working only on the paper for the first part. And I wanted to thank you all for your attention. So, and also a little small advertisement they asked me for. So don't miss the next science hour, which will be in April about Work Package 7. Still to be confirmed the speaker, what they will talk about and the date, but just check the ED website and social media for more information. And I think I get more or less half an hour. So now if you have any question, I have also some more plots that I haven't shown, but maybe I went too fast, but let's open the discussion here.
Well, and yes, we can, give you a round of applause. Thank you very much. And it's very nice to see that you have those two parts of your talks that you are already into the study of these water hosing experiments that we are really expecting to see before we can make decision about what else to do or what different to do in ERIC. You can perhaps start. I don't know whether I see very well who is raising an hand. Kat Grayson?
Yeah, hi. Sorry, can you share your slides again, Eneko? Can you hear me?
Yeah.
Sorry, this is probably a really basic question, but where you have your density profiles where you show salinity and temperature.
Yeah, these ones.
Yeah, where does this data come from for your models? Because your resolution is you said you had like 18-kilometer resolution. So how do you get such detailed profiles from your models?
So these profiles are the average in this box. So it are not profiles of just a grid point. Yeah, I don't know then the levels. It's the NEMO level, so it's 76 level. I don't know if any. So
okay,
you mean? Yeah.
Just like the vertical resolution, like how you get such like detailed vertical resolution. Even I know it's an average, but I didn't think you had such high resolution in the vertical.
It's very high resolution near the top. It's 1 meter at the top.
Yeah.
Ah, okay, thank you.
Yeah.
But
Okay,
yeah, no, sorry. I have another question, but maybe, yeah, if nobody else is raising their hands. Do you have another question, Kat, or I have a question?
No, that was it. Sorry, I didn't realize it was 1 meter resolution. I was a bit confused where that came from. But yeah, thank you.
No.
So, I mean, I have a question. I mean, you seem to focus all your analysis on correlations with the mixed layer in the Labrador Sea. But somehow this is only one part of the AMOC variability. So have you considered, I mean, are you putting yourself in a framework where you say, okay, I know it's only part of the AMOC variability, but I study that part? Or do you have you looked, for example, in your model that your model perhaps is too much influenced by the Labrador-C convection compared with reality?
So yeah, we wanted, so the idea of my thesis is more to focus on the mixing. So that's why we didn't look at other processes impacting the AMOC. So, and then when we started, I made some analysis with empirical orthogonal functions about the mixed layer depth. And when taking this box I use and when correlating the first principal component of the mixed layer depth EOF analysis, we have a very strong correlation about 0.94 or 0.90 whatever. So this was telling us somehow that seems that the main driver of so the main mode of variability in the mixing it's there, and we just take the box average because it's quite more better indicator. But yeah, we didn't really take a look on the, for example, on the Nordic seas, which could be also important for the bottom waters that come to through the between the Greenland and Iceland. But we see that there is also not really a mixing in the very high resolution model, because in fact there is a bias on sea ice that the region is more covered by sea ice. So if you remember also the plots from the average climatology, let's see if I can. If we take a look on the average climatology, we see that meanwhile in the observation seems that we have very strong mixing. We have
Well, it's not.
mixing on the low resolution one, but in the high resolution we almost have no mixing there.
Yeah, I mean, I'm not sure. What are you using the same criterion for the mixed layer depths in all? Because I mean, such a big patch of mixed layer to 2000 meters. Well, maybe it's realistic, but it looks like perhaps it's a bit exaggerated in EN4, depending on the criteria.
Yeah, the criteria I use for all of them except for Argo, which is already provided by them and it's not directly comparable at all, is that I took monthly temperature and salinity, 3D temperature and salinity at monthly basis. So I did this just to compare with the observation. Then with this monthly data, I compute the sigma 0 density with the TOS10 equation of state. And then I use the density threshold algorithm to compute the mixed layer depth, setting the density threshold to 0.03 kilograms per cubic meter and to 10 meters, so which is the common one. This is the fact is the definition that it's used for instantaneous when computing the mixed layer depth from instantaneous data. So maybe yeah, it's true that for monthly average, maybe we should have a, I don't know, a lower, but in any case, it will be comparable between all of them.
But I mean, it means that really because you have used the same criteria, so this means that, yeah, your model is too stratified compared with the observation clearly. So, yeah.
Yeah. Yeah, that will be. Also, computing the mixing, it's not really. So a small change on the stratification could make a big impact, but yeah, it's true that the stratification of the EM4, it's, I don't know.
But
Seems
that's
quite
subpolar size. That's the Labrador Sea. That's not the Nordic Seas.
yeah, that's true.
But when you take a big box like that, you have all the very stratified water that is around the convection region. So in fact, you do get this strong stratification at the surface, but in reality, it's all around the patch that is convecting. It's not in the convection site itself.
Okay. Yeah. So
May I ask a question?
Oh, yes, please.
Hi, thanks, Eneko. It's a lovely talk that you have. So actually, it does tie to what Anne-Marie was asking, because if we see from your figures, there's quite a bit of mixing or convection going on the eastern subpolar gyre region. I guess then the question comes, you said you had a really high correlation with the Labrador Sea. On what time scales, like how long of a time series did you use? So basically, what time scales are you getting such that it has such a high correlation? Because from what we've seen in some of our runs is that the correlation, as you get into higher and higher resolution, the relationship between mixing or the convective sides with the AMOC itself tends to go towards the eastern side. So like similar to yours, our low resolution has high relationship with the AMOC, but as you go towards higher and higher resolution, it goes towards the east. But the problem is this high correlation that we see, or high covariance that we see, is much more on the interannual timescales, or on timescales that are much shorter. Whereas like if your time series is really long and it encompasses a few decades or so, then the high correlation tends to be with the Labrador Sea side. So I guess the simple question is, how long was the time series that you had?
So yeah, the experiment is 66 years long. So the data we are using is 66 years. So
60 years?
Yeah, 66.
Okay, 66.
So the thing is, the AMOC, we computed it only with annual data of the AMOC and March mixed-layer time series. We tried using some low-pass filters of 3 and 5 years, but we cannot go to filtering like for more larger time scales because we end up without enough point to get significance.
Right. Okay.
So we try to fit to more low time scales. I don't know if you have any suggestion with that.
But I think you have shown one plot, which was, I think, the AMOC with itself at 1,000
Right.
meters. And it almost looked like the low resolution ones. They produced more low frequency variability than the high frequency. The high resolution one, the very high resolution one, it almost shows this quasi oscillatory behavior. So it's very strong on really interannual time scales. Whereas, the time scale look longer for what you are capturing for 3P and to some degree HR, right?
Yeah, it's true that we had this kind of oscillation on the very high resolution.
And it's more confined to the north, it seems, right? Where the other is sort of more extending across the North Atlantic.
Yeah.
Do you have perhaps something like this, but instead correlated with your mixed layer depth? Because here you're showing, here you show the coherence for AMOC, but the relationship of your mixing, yes.
This one.
So it's still quite similar.
Yeah, it's quite similar. The impact is not so strong. We see nice propagation in the HR model, but only in the sigma space. But in the case of the VHR, we have almost nothing, and in the low resolution one, we have almost no significance. So probably, maybe this could be due to the method I used to remove to correct the degrees of freedom, because as they are really autocorrelated, in particular the AMOC, probably we need strong correlations to make it significant.
What's your time window again that you used to filter this?
So this is only yearly AMOC with March mixed-layer depth time series.
But did you apply any like low pass filter, like a 5-year running mean or 3 years? No. So this is pure, just March. Okay.
Yeah.
I have another question. Could you go back to your first plots, the one about the standard deviation of the mixed layer depth? Yeah, I was really surprised that the very high resolution model has a smaller standard deviation than the low resolution, because both have more or less the same kind of mixed layer itself, right?
Yeah.
The mixed layer is about the same in the 1 degree and the 1/12 of degree models. That was the previous slide. And then if the mixed layer itself is the same, what does this mean? That it's not, the standard deviation is lower when you are at high resolution? I find difficult understanding that. I mean, how is it computed? It's from the monthly values or from the...
Yeah, it's from the monthly values and only for March.
For the month of
So-
March. So you
Yeah.
take all the months of March in your 76 years,
Yeah.
and you have less interannual variability in
Yes.
these years in the high resolution model. I mean, I really... Could you show the previous slide again, the one with the mixed layer itself? I mean, see, it
Yeah,
looks like it's even a little bit stronger, deeper in the very high resolution model. So if it's deeper, and then it's such a high resolution model, the standard deviation should be bigger. I mean, that's looks strange.
Yeah, this means that we maybe have almost the same mixed layer depth for all the marks, like tips. And don't know, but probably this can be explained with the profiles.
Okay. Do you have the time series?
I don't know. It's off.
I think with the time series we would be able to tell what's happening, because I don't remember very well, but I think that for the eddy-rich version there wasn't almost no decadal variability, so that would reduce in the end the variance that you can get. But we can get back to those and see.
Oh, so I mean, that would be something very interesting, right? The fact that in this control run, you would have much less decadal variability at high resolution compared to the low resolution. That is certainly worth investigating.
Second part we can-
Hi.
we can check.
May I? So, hi, Isaido, can you hear me?
Yeah.
Yeah.
Yes.
Yeah, sorry. So perhaps the low resolution model, I think, is a little bit misleading because it has a huge sea ice concentration bias in the lower seas. It's almost entirely covered by sea ice, and then it has very little convection. So it seems like some changes in the sea ice can allow more mixing to happen, and that's why perhaps this that's the decayed variability, multi-decayed variability is connected to that. So I will be very cautious with the results of the low resolution model, because it's very unrealistic, and the analysis has really big bias, and so it's the same problem that we had in the CIMIC 6 model configuration. So yeah, I wouldn't be like thinking that the low resolution model is anything but realistic, or yeah.
Yeah, okay, but still the ECEarth very high resolution has less standard deviations than EN4 for the recent years, for example. So there may be perhaps too much decadal variability in the low resolution, but perhaps some missing in the high resolution.
There is one mismatch there that I see. That is, we in the simulation we are computing the standard deviation with 76 years, and EM4 it's considering only 20 because we wanted to center around 1950. So it's not representing the same time scales. It cannot represent multi-decadal variability in EM4.
Well, you are missing the fourth component, but you have all the internal variability of the climate, right?
Yes, I know, but if you have only 20 years, you are not including variability that goes beyond a decade. No, and in the simulation, we do have that variability. So if they, for example, if you think of a trend that manifests over 20 years, in Neon 4, it's gonna dominate the variability. But in the simulation, it can the long-term trend might be much smaller, no? And that's something that we might need to double check.
Yeah, perhaps you should detrend EN4 to compare with the control one.
Yeah. Also, what I see, not only the trend, but also EN4 could have, in particular in the 1940-1960 period, a lot of errors due to the observations how were done, because there were like fewer observations and also bigger error in the measuring tools. So at the end, everything that is 3D in the ocean, it's tricky when you go back on time.
I mean, your Labrador sea ice problem, I mean, it's not that you have on average more sea ice there, but this is sort of episodic, right, in these climate models. So sometimes it comes, it freezes for decades and years, and then it unfreezes again. And if you have this kind of signal in your time series, this will dominate, I guess, quite a bit of your analysis, and you will get quite a bit of low frequency variability included in this, unless you have a steady, a state where the system is frozen all the time. But I think that the modeling systems that have this Labrador Sea problem, they quite often have this just episodically, right? And then yeah.
So I see that the hour is almost up. So I don't know what is the idea there, Thomas? Is it possible to continue discussing for those who wish to continue to ask questions? I still have a number of perhaps more technical questions, or should we stop there?
No, I think we are. It's in a way fortunate that this is sort of the last, probably for many, the last appointment of the day. So in principle, nothing stops us from going on, right?
So I would like to thank everybody for having come, and for those who wish to stay, who has questions about the first part of the talk, because then I have some questions, but that are perhaps more technical and perhaps less interesting for other people about the posing experiments and their analysis. So perhaps we could. Oh, so Thomas.
Yeah, I mean, just a little one. I mean, for me, when I've looked at the results, it wasn't always clear something like a linear story, what you would think, sort of having to parameterize eddies, then permitting, and then resolving them. And, there may be many reasons for this, freezing in the Labrador Sea, short time series. But I'm wondering also to what degree, differences in atmospheric resolution have a role to play as well, because, a high resolution ocean that has lots of energy on mesoscales, can have also an impact on the ocean as well. So it's always, it's challenging to disentangle this and then trace this all back to the, to the role of eddies. I think that complicates it a bit. But I thought it is a bit of it's not a super straightforward story, and probably there are many reasons as to why this is, unless you push me back on that. But again, sort of, it wasn't always obvious. You see this, and some linear story. It was quite often not that obvious, right?
Yeah, I completely agree. That sometimes it's difficult to differentiate which improvements we have thanks to the increase in the resolution of the ocean, and which are to the atmosphere, and in particular in those processes that we also have the atmospheric forcing taking part. So yeah.
So yeah, I then move to more technical question. So that's on the second part of your talk. And it's about your strange pattern of the difference between the AMOC in the runs with housing versus the control. You know, you have this strange pattern at 36 north or something. No, it was this slide. So first, I would like to know what you are doing with the Mediterranean Sea when you compute your AMOC.
We don't take into account.
So you stop at Gibraltar.
Yeah.
So this means that there you are missing some overturning. You have some kind of boundary conditions there. But yeah, I mean, there are two things that I think. I mean, if you look at your control, you do see that you have kind of extremas between 30 and 35. You have some features that appear there. So I can imagine two things. One would be the Mediterranean Sea, and the other one would be perhaps the Gulf Stream separation and the fact that maybe by working from monthly averages, you are missing a piece of the. But you don't know. It's not true because you don't have eddy correlation when you are in depth space. That's only true in density space. So in depth space, yeah, I mean, I wonder whether this could have to do with the Mediterranean Sea.
Yeah, we have this question again also because we saw also this kind of strange pattern at 35 degrees north when doing the correlations that with the mixed layer depth with the AMOC and some of them here. Yeah, we have also this pattern here and here, which was also wondering us what's going on. So there, it's strange because I think that the first AMOC we had, I don't know if we had an AMOC with the Mediterranean, but I will try to compute it with the Mediterranean. But at the beginning, what we thought it was is that it was more related to the Ekman transport, and we were able to remove part of it, but not at all. So I don't know, for example, in this case, if we remove the Ekman transport, will make a difference? Probably yes.
Or that would be because it's where the Yakman transport is maximum, that you see it between 30 and...
It will happen as well that if there is some phase that you have 3 or 4 years in a row or in this long interval with a strong winds in the water housing but not in the control or the opposite, could happen. It's an interesting thing to do check both including the Mediterranean and also check removing the Ekman transport if the difference change a lot or not. Yeah, thank you for the suggestion.
We initially, not for this experiment, for the control, yes, the first time we computed the AMOC, it had very strange features, and then we had to double check quite precisely what we were using, the Lancy mask that we were applying.
Yeah.
And we had to remove, if from what I remember, we had to remove the Mediterranean Sea to have something a bit more sensible.
Yeah. We have more issues in the Caribbean Sea, but no. I mean, currently, in fact, I'm not using a Lansing mask anyway. I'm using a zip file because we use a symbol tool to extract the region and do everything. But yeah, I don't know. We can try to go back and check the Mediterranean. It's quite, now that it's quite fast to compute. and see if we have any change. And also the Bergman transport. The only thing is that we didn't have enough time to go deeper in these patterns because, as I said before, this figure is from this week. So
you have the one with the last 10 years.
yeah, I have the one with the last 10 years. Maybe it will take a little bit time.
Well, he's finding the figure. I guess for me, the main take-home message from this initial analysis is that we are not succeeding in inducing a collapse of the AMOC. We are not even close. All the 3 experiments show a decline compared to the baseline, but I don't know, we need to compute the trends just to see how much of a reduction we're getting, but I don't think it's stronger than a 10%.
And
So
you have, oh, sorry, you have 0.1 sphere drop for the strength of the housing.
Yes.
So that's pretty strong compared to Greenland melting, but it's not the strongest that they propose in OMIP, in HighResMIP, that you could use 0.3, that would be even stronger. But I'm not sure I see the point of doing that in a high resolution model, something which is really very unrealistic compared to Greenland melting.
Yeah.
So
an important difference is that we are doing this in a 1950 relative forcing state that has a much more stable AMOC. No? So maybe if we had done the same in a future context, no, we would see a bigger impact. The problem is we couldn't run different members from the historical that we have that would start from the same point because the first 5 years would be just to build them for the trajectories to diverge, and we didn't have so many resources to complete the experiments. But there are a few lessons that we can get from this to inform any other potential water housing experiment in NERI. For me, one of them is it should be a longer experiment. 20 years is not enough because there is a cumulative effect of the freshwater melting. The other is it would be better in a climate scenario context because there would be then 2 contributions to the AMOC weakening. No, the warming of the surface that would reduce the stratification, plus the freshwater forcing that would do the same.
well, I mean, in our study, I don't see whether you have read this paper, Marion de Villiers and Didier Swinguedoux. I think it's 21. So what she did was a 20 ensemble member with the IPSL model. So that was a 1 degree model, low resolution. And she put a housing that was similar to Greenland melting. So it was realistic and in a historical setting. So it was with climate change included. And she said that in fact, the effect was very, very small. But so she was putting less water than what you are doing.
We discussed this exactly with her, and she's the one that recommended us to induce a stronger melting if we wanted to see an impact, precisely because of her results. Yes, this plot is comparing the last 10 years, so that should minimize the
variability.
The pollution, let's say, from the Ekman signals. And we see it's a little bit reduced, maybe not so much for the third experiment.
Yeah.
Yeah. So in fact, the question is for Erie, what are we after? Because clearly, probably if we want to stop the MOC in 10 years, we have to hammer it strongly, like what Laura Jackson did with the HighResMIP model. So that's completely unrealistic. And then if we don't go for a collapse, but we just want to see how the decline may be different in a high resolution model, then what are we after exactly?
In work package 6, I don't think we committed to kill the AMOC. No, we just wanted to see the effect of the meltwater fluxes. So we could go for something that is closer to the expected melting. In work package 8, we have the storyline about the AMOC collapse, and that's a different story. Maybe we'll need to revisit that and think of something else that could also be insightful, because I'm not sure we can come up with a protocol that will ensure that we are killing the AMOC. At least using a reasonable amount of clearing resources.
So, I mean, it would be interesting to do the same study as Marion did. The effect on AMOC itself may not be very big, but we may see interesting things in terms of response in the ocean and perhaps impact on Europe, I don't know. But yeah, it would be difficult with few ensemble members.
I would concentrate on the effects on water mass transformation, on how the freshwater anomalies end up impacting the mixing, because the freshwater fluxes are released just by the coast, and the mixing doesn't happen at the coast, so things like that. Then the climatic impacts, I don't think with a 30-year simulations will be able to tell much, and that's a shame for work package 8, but I don't think that's needed for work package 6.
And what do you think? I mean, here you are doing the hosing in a control run. What would be the most interesting for Erie? Do it in a historical run like Marion did, or imagine that Greenland is going to melt 4 times faster or something like that in the near future, and just do it as a scenario?
So we could do I think it makes sense to do like a scenario that accounts for the expected melting, and maybe another scenario that accounts for twice as much or 4 times as much, so if we could afford 2 experiments, I would just look at the sensitivity to the forcing, but always in a climate scenario context, because that would be revising the current knowledge that we have, including an important forcing that is currently misrepresented in the models.
I'm not sure if it's ever been done. Is it been done in scenario runs? Putting some Greenland melting? Yeah. We should look at the literature, because if it's never been done, maybe it's worth doing it.
I doubt it's never been done, but I'm sure someone has that. If not Didier, Laura, Jackson, yeah, someone has done it. But we can check.
Okay. Well, I think there are no other questions. I don't see any hand raised. So, I mean, thank you very much, Eneko. This is really very exciting work. And yeah, let us know when you have a a paper submitted. We will be very happy to read it.